Hello, everyone, and welcome to the CHEM100 lecture on periodic table, atoms, ions, and Lewis structures. Starting with the periodic table, we had two scientists, Dmitry Mendeleev and also Lothar Meyer. They were in two different countries and published nearly identical periodic tables of the elements. Now, this is fairly provocative when you think about the fact that at the time there were no cell phones, there was no internet. And so these two scientists really couldn't communicate, yet they both independently in two different countries published nearly identical classification schemes for the periodic table. These schemes were based on the physical and chemical properties of the known elements at that time. And then later, Henry Moseley established the periodic table that is more current and more similar to the one that we use now. On the test, I don't ask for these names or these dates. I just want to bring this to your attention because we're talking about way back in the 1800s and chemical and physical properties being used by both of these scientists, yet elucidate periodic tables that are nearly the same without ever communicating with one another. We'll start talking about atomic structure by addressing the subatomic particles. There are three types of subatomic particles that we're going to talk about in this course: protons, electrons, and neutrons. You notice that I give you masses for the protons, electrons, and the neutrons, not so much that you memorize them. I'm not interested in having you memorize them. I just want to use them for a little bit of reference to talk about the structure of atoms that's based on the subatomic particles. The protons, you notice, have this 10 to the minus 24 grams, and also neutrons 10 to the minus 24 grams. 1.673 and the decimal places go on for a proton, and 1.675. So these masses are very, very similar to one another. Both of these subatomic particles are in the nucleus, while the electrons are outside of the nucleus in what we call the electron cloud. When you look at this mass, we're talking 10 to the minus 28 grams. So the mass of an electron is negligible compared to that of a proton or a neutron. In fact, protons and neutrons are nearly 2,000 times heavier than an electron is. And when we talk about where these subatomic particles are positioned, again, the positively charged protons are in the nucleus, and the neutral neutrons are also in the nucleus. While the electrons are outside of the nucleus, this is considered to be extranuclear subatomic particles. So the heavier, or those subatomic particles that have more mass, are contained in the nucleus, while the electrons are contained in what we call the electron cloud. Outside of the nucleus. So if we talk about this a little bit further, that tells us that the protons and the neutrons give an atom its mass, while the electrons give an atom its volume. More electrons, we have a larger atomic radius, or a greater volume. Protons also are derived from the atomic number of an atom. So the atomic number, as shown on the periodic table, equals the number of protons. And if you have a neutral atom, and all elemental atoms that are shown on the periodic table are neutral, this also tells you the number of electrons. Protons give an atom its properties, its chemical properties, and elements don't lose or gain protons because this changes the elements. The only time you see elements losing or gaining protons is in nuclear chemistry. And we don't discuss nuclear chemistry in this course per se. But even with nuclear chemistry, if an elemental atom loses or gains protons, it becomes a different element, a completely different substance. So when we talk about chemical reactions at this level, again, excluding nuclear chemistry, we're talking about gaining or losing electrons. And it is a gain or loss of electrons that causes a chemical reaction to occur. Neutrons can vary associated with an atom. For example, carbon has C12, C13, and C14. And these are different isotopes that are associated with carbon. And each of these isotopes has a different number of neutrons. Again, elements in the free state are neutral. And if you have a neutral element, you have equal numbers of protons, that is equal numbers of positive charges, to electrons, that is equal numbers of negative charges. The nucleus of an atom is a very small, dense, positively charged center. The nucleus contains the protons and the neutrons, that is the positive charges, and we designate those charges as +1. They're not exactly +1, but we round the number to +1 just to make it easier for us to analyze and evaluate atoms and chemical reactions associated with atoms. The neutrons have a neutral charge, so there is no charge on the neutrons. So that means that the nucleus is positively charged. The nucleus concentrates almost 99.9% of the atomic mass because it contains, again, the heavy subatomic particles, the protons and the neutrons. The extranuclear, or the outer atomic region, contains all of the electrons, and we often call that an electron cloud. The electrons move very rapidly around the nucleus. They are negatively charged, and they are attracted to the positively charged protons in the nucleus, which maintains the atom structure. Again, the extranuclear region accounts for the atomic volume, or the atomic radius. So the more electrons you add, the greater the atomic volume, the greater the atomic radius. As I just mentioned, there are two types of charge. That is the positively charged proton, which we designate as +1, and the negatively charged electron, which we designate as -1. Unlike charges attract, and so if we had, for example, a proton and an electron, the two species would move closer together, decreasing the distance between them. There's an attractive force here. And as the distance decreases, that attraction force increases. Like charges repel. So suppose we had two protons. Those charges are going to want to stay apart. But if we force them together, as the distance between them decreases, and again, this is a repulsion force. As the distance between them decreases, the force increases, albeit not an attractive force like the proton and the electron. It's a repulsive force. But again, the distance decreases between them, the force increases. Similarly, if we had two electrons, and we started forcing those two electrons closer and closer together. As that distance between them decreases, the force increases. And in this case, the force is repulsive. Atomic mass is a weighted average. The atomic mass is the average of all isotopes. And so as I was telling you, With carbon, for example, we have an isotope called C12, an isotope called C13, and an isotope called C14. The difference between these three isotopes are the number of neutrons that each has. So C13 has 1 neutron more than C12, and C14 has 1 neutron more than C13, or 2 neutrons more than C12. We use the C12 as a reference for atomic mass. And atomic mass is given by AMU, that's called atomic mass units. 1 atomic mass unit equals 1/12 the weight of C12. Again, C12 is just a reference point, so try not to make this more difficult than it is. We use sea level as a reference point for altitude. For atomic mass, we use C12. If 1 atomic mass unit is equal to 1/12 of the weight of C12, that means that C12 is equal to 12 atomic mass units. These two statements are saying the same thing, just in 2 different ways. That also means that an atom that's 2 times as heavy as C12 is going to be equal to 24 atomic mass units. What if we had an atom that is 1/2 times as heavy as C12? Then that atom would have atomic mass unit of 6. We can keep track and actually calculate the subatomic particles or the contributions of the subatomic particles if we have a certain amount of information. Now, the atomic number, which is designated by this uppercase Z when we're using these kinds of calculations, and we use these kinds of calculations in what's called isotopic notation. So Z is the atomic number, and we can get that atomic number anytime we want from the periodic table. And you will always have a periodic table available when you're taking exams. And even as we move further through this class, starting now, you're going to start having an periodic table available for you when you take quizzes as well. So from the periodic table, we get the atomic number, and that gives us the number of protons in the nucleus. It also gives us the number of electrons, because in a neutral atom, the number of protons is equal to the number of neutrons. And every atom that's depicted on the periodic table is neutral. The mass number is given by this uppercase A, and the mass number has to be given to us because we don't know what isotope we're talking about unless we're looking at the periodic table. If we're specifically looking at the periodic table, that's giving us the atomic mass units in an average value for all the isotopes of that particular element that are found in nature. But if we're looking at one specific isotope, we have to be given the mass number because we don't know what specific isotope that might be. We do know that the mass number, A, is equal to the sum of the protons plus the neutrons. That gives us the total mass because remember, these are the 2 subatomic particles in the nucleus that represent the mass of an atom, because the remainder of the atom is the electrons, and the mass of the electrons are negligible, some 10 to the minus 28, compared to 10 to the minus 24 for the protons and neutrons. We can calculate the subatomic particles because the number of protons is equal to the atomic number Z. So again, that comes from the periodic table. The number of electrons is equal to the atomic number Z if you have a neutral atom. And again, we can get that from the atomic number on the periodic table. The number of neutrons is equal to the mass number minus the atomic number. So in other words, uppercase A minus uppercase Z. And again, we need to understand what the mass number is, and we need to be given that value. Isotopes are differing atoms of the same element. So we're talking about the same element. When I talked about C12, C13, and C14, I was talking about carbon. All isotopes of the same element have the same number of protons and the same number of electrons, and therefore they have the same physical and chemical properties. It is the number of protons that gives an elemental atom its chemical and physical properties. But isotopes differ in the number of neutrons. And because they differ in the number of neutrons, and neutrons are one of the subatomic particles that gives an atom its mass, then we're going to have different atomic weights associated with different isotopes of the same element. Carbon, for example, again has C12, C13, and C14. C12 and C13 are both stable isotopes, but C14 is radioactive, or we could call it radiogenic. Hydrogen, you have protium, that's H1, deuterium, that's H2, and tritium is H3. Protium and deuterium, although deuterium is heavier than protium, they're both stable. But you can see tritium is radioactive, or we call that also radiogenic. We can use isotopic notation to depict how a particular isotope is going to appear, what the atomic number is, what the mass number is, and we can calculate how many neutrons that particular isotope has, given the mass number and obtaining the atomic number from the periodic table. So looking at this particular isotope, you can see that we've added something to this notation, and that is the charge. So previously, we didn't have a charge because we had a neutral atomic element. Here we have a charged species. Whenever you have a charged species, that's called an ion. So when we look at this ion, we don't have the same number of electrons as protons because we have a positive charge. That positive charge means that we have given up or lost electrons. Now let's evaluate the structure a little more closely. This 20 represents the atomic number, which equals the number of protons. And if this species were neutral, it would also equal the number of electrons, but it's not neutral. It has a +2 charge, which means that it has given up 2 electrons. So if it were to have 20 electrons when it's neutral, but it has given up 2 electrons because it has a +2 charge, that means that we have 18 electrons in this particular isotope of calcium. We could also calculate this mathematically. Like you see here, we know that we have 20 electrons if neutral, and we have given up some number of electrons that we're going to designate with X, and that resulted in a +2 charge. So if we add X to both sides and subtract 2 from both sides, and there are other ways to do this algebra, this isn't the only way, but we get 20 minus 2 equals 18, and so X equals 18 electrons. The easy one here is the neutrons. So with the neutrons, we're going to take the mass number, and the mass number is the number of protons plus the number of neutrons, we're going to subtract the number of protons, and that leaves us with 25, which is the number of neutrons that we have. Now, it doesn't matter to me whether you want to look at electrons intuitively, like I have done on the bottom, or if you want to do it using algebra, using math. Either way that you want to be able to calculate, I would prefer if you could eventually look at this intuitively and understand it that way. But either way that you want to look at it is fine. Here's an example that we're going to try. And they're asking for the protons, the neutrons, and the electrons, and then also how many electrons to make this neutral. So we see that we have the mass number again, which is the number of protons plus the number of neutrons. We have the atomic number here, which is just the number of protons. And then we have a charge. So this is an ion. If I could spell. Okay. So the number of protons is going to be given by the atomic number that we get from the periodic table. And in this case, that's going to be equal to 8. The number of neutrons is given by the mass number, which we know is 18. We're going to subtract the number of protons, and that leaves us with 10 neutrons. The number of electrons, now this is a little bit more difficult when we think about if this species were neutral. If it were neutral, then the atomic number, which equals the number of protons, would also equal the number of electrons. Again, if it were neutral. So we answered this question, that would be 8. But we have a -2 charge, which means literally that we have gained 2 electrons. So if 8 would make us neutral, and we've gained 2, that gives us a total now of 10 electrons. We've talked already about the classification of elements, and I gave you this breakdown between metals and nonmetals, and you can go back to the previous lecture, but I would expect you to start thinking about aluminum foil and all of the characteristics that aluminum foil has to explain all metals, with the exception of mercury, because mercury is liquid at room temperature, but otherwise has similar characteristics to all other metals. And then the nonmetals just have opposite characteristics of aluminum foil. This particular periodic table gives you a breakdown of the metals and the nonmetals. You've seen it before. I've shown it to you before with polonium and aluminum being the only 2 metals that are touching this red stair step here, separating the metals from the nonmetals with the metalloids, which have characteristics somewhere between metals and nonmetals. Elements are arranged in order of increasing atomic number. So let's just go back one slide and have a look at that. And you notice that we start here with hydrogen and then go all the way over to the other side, we have atomic number 2. If we go back to the left and we read left to right, now we have atomic number 3, then 4, then 5, 6, 7, 8, 9, 10, and the atomic numbers just keep going up, left to right and bottom to top, sequentially on the periodic table. The next bullet says elements having similar chemical properties are positioned in vertical columns. And if we look at the vertical columns, those are called groups, columns, or families. We also have periods, which are horizontal rows of elements in the periodic table. And so when we go across the periodic table from left to right, for example, this is row 1 as we go from hydrogen to helium. This is row 2 as we go from lithium all the way over to neon. These are called rows or periods. And then the groups, columns, or families, for example, group 1A is here from hydrogen all the way down to francium, and group 8A is here from helium all the way down to radon. If we take any of these groups, columns, or families, every vertical column is going to be another group, column, or family all the way across the periodic table. Those species that are in the same row, for example, every species that's in row 2 has the same valence shells. And those species that are in the same group, column, or family, for example, if we looked at group, column, or family 2, or we also use a Roman numeral for it, 2A, they all have the same number of valence electrons in them. So this particular slide is showing you the rows or the periods, and it's pointing out in particular row or period 2 and row or period 6, but it could very well point out row or period 1, 3, 4, 5, and 7 just as well. It's just pointing out those so that you can get a clear picture that a row or a period goes all the way from the left side of the periodic table to the right side of the periodic table, and those species, those elements that have the same row or period number have the same number of valence shells. There are 4 groups that we are going to discuss that have common names and numerical names. So group 1A, that's the numerical name, are also called alkali metals. That's the common name. They're soft, shiny metals, and they're highly reactive with water. In fact, violently reactive with water. If you put sodium or potassium in water, it will start to spark and make flames. And if you put enough sodium or potassium in water, it will explode. This group, even though hydrogen is in group 1A, hydrogen can act like a metal, and hydrogen can sometimes act like a nonmetal. It's not a metalloid. It just has the ability to act like either a metal or a nonmetal, and so it's excluded from the alkali metals. It's not excluded necessarily from being a group 1A, but it is excluded from being an alkali metal because it has this nonmetal capability. Group 2A are also called alkaline earth metals. That's their common name. They are also soft and shiny, and they're moderately reactive with water. They're not as violently reactive with water as alkali metals are, but they're reactive with water. And if we go all the way to the other side of the periodic table, group 7A has a common name of halogens. And the halogens are reactive and they're colored, and we'll talk about why they're so reactive. They're colored, for example, bromine has a brownish yellow color to it. They're gases at room temperature or slightly above room temperature. And then we have group 8A, which is the noble gases. And the noble gases are very stable. and unreactive. And unreactive is called inert. That's the term that we use for it. They undergo very few, if any, reactions. And we'll talk about why when we talk a little bit more about their group, column, or family and the electrons that are in their valence shell. So this periodic table is pointing out to you where these 4 groups that we just talked about are. And so you can see the alkali metals are here in group 1A. And then the alkaline earth metals are here in group 2A. The halogens are over here in group 7A, and the noble gases are in group 8A. Now, what I want you to notice first is that the noble gases have 8 electrons in the valence shell. And it turns out that having 8 valence electrons in your outermost shell, which is your valence shell, means that you're stable, means that you're inert or unreactive. And so if we look at a situation like that with group 7A here, group 7A being right next to group 8A doesn't have to change very much in order to become stable. So it would be like if you wanted to buy a new Mercedes or a new BMW or a Maserati and you had all the money you needed except for $1. You would be digging through the couch cushions or trying to find aluminum cans or anything that you could to get that $1. You'd be desperate to get that $1 so you could just go pick up your brand new car. And it's not much different with the halogens, because the halogens being in group 7A have 7 valence electrons in their valence shell. In other words, in order to be completely stable, all they need is 1 more electron. So they'll do pretty much anything in terms of chemical reactivity to get that 1 more electron so that they can become stable. For example, fluorine, which is right here, has 7 electrons in its valence, and it wants to have the electron configuration of neon and have 8 electrons in its valence. In order to do that, neon is right next door. All fluorine has to do is gain 1 more electron. If we look at the other side of the periodic table over here with the alkali metals, and we can see lithium is right here. Lithium wants to have the electron configuration of the noble gas that's closest to it, which would be helium over here. Thinking about the atomic number that's associated with lithium, it's number 3, atomic number 3. And helium is, I'm sorry, I don't know why this won't stay. It's giving us a little trouble here, is number 2. So all essentially lithium has to do is give up 1 electron, and it can have the electron configuration of helium. Now, helium is the 1 noble gas that is stable with 2 electrons. All the other noble gases are stable with 8 electrons. You're not going to be looking at a periodic table that is labeled like the one on the previous slide. You'll generally be looking at a periodic table that looks like this one. But you notice that you still have all of the atomic numbers. And the other thing that I want to make you aware of is that you still have all the group, column, or family numbers at the top of the groups and columns. And so when you look at this, you'll be able to know how many valence electrons there are associated with every group, column, and family because of those numbers. We're going to be paying attention to the A's, all of the groups that have A's associated with them. And those groups are all called representative elements. They're called representative elements because they behave very chemically characteristic. And so we can predict their chemistry fairly straightforward. These with the B's in the middle, these are called transition elements. And the transition elements we can't predict quite as easily. So we'll talk more about the transition elements later on. Sorry, these slides are still kind of flipping around for some reason. I don't know why. We'll talk more about the transition elements later on. For now, we're going to focus on those representative elements. And the thing with the representative elements that we need to know, or with any of the elements we need to know, is how many valence electrons do they have? In other words, how many electrons in their outermost valence shell, because those are the subatomic particles that are going to be involved in chemical reactivity. And the way that we find that out is just by going to the top of the group, column, or family, and you see this is group 1 or 1A, and that means there is one valence electron in the outer valence shell for every species in that group, column, or family. Group 2A, same thing, 2 valence electrons in the outermost shell for every species in that family. We go across the periodic table. Over here, group 3A, 3 valence electrons for every species in that group, column, or family. And then 4 valence electrons, and then 5, and then 6, and then 7, all the way over here to 8 valence electrons for group, column, or family 8. And this one, remember, turns out to be stable. The only species in that group, column, or family that doesn't have 8 is helium. Helium has 2, and it turns out that 8 is called an octet and 2 is called a duet, but helium is the only one with the duet. Now, how do those valence electrons relate to Lewis dot structures? And we draw Lewis dot structures as a model because we can't see atoms, and we want to be able to discuss atoms. So we have the Lewis dot symbols from the Lewis theory as a model to be able to draw atoms and look at the bonding patterns that are associated with forming compounds. We only draw the valence electrons. And so according to the periodic table, hydrogen is in group, column, or family 1A and has 1 valence electron. So when we draw hydrogen's Lewis dot structure, we draw it like this with 1 valence electron, and anything else like lithium or sodium or potassium, everything else, in fact, that's in that group, column, or family is going to be drawn with its single valence electron. We go to group, column, or family 2A, then those species are going to be drawn with their 2 electrons, their 2 valence electrons, and remember, electrons repel. So we're going to draw them as far apart as possible, and that puts those 2 electrons 180 degrees away from one another. If we go to group 3A, then we will show the symbol for each one of those atomic elements with 3 valence electrons drawn around it, like boron and aluminum here. Group 4A, carbon and silicon, we'll draw 4 electrons, and we'll draw them all the way around this structure, as far apart as we can get them. Group 5A, there are 5 valence electrons in the outer valence shell, and so we will draw them 1, 2, 3, 4, as far apart as we can get them, and then we will start pairing them up. Group 6A, there are 6 valence electrons, and so again we will draw them 1, 2, 3, 4, surrounding the structure as far apart as we can get them, and then we will start pairing them up. Group 7A, all of the halogens, 7, so we will have 3 pairs and then 1 unpaired. And then of course group 8A, which we're not showing helium, but we could. and helium has 2 electrons, so we'll put one on either side of it. All the rest have 8 electrons, and again, that is considered to be the stable electron configuration. In other words, every atomic element on the periodic table wants to have that stable electron configuration of the noble gases. They will be reactive until they get that electron configuration, either an octet or a duet. Once they have that stable electron configuration, they will not be reactive anymore. Again, if we look at the periodic table, we can transfer all of that information to this periodic table simply by looking at the number of the group column or family and by looking at the row numbers so that we know what shell we have. So we have shell 1, shell 2, shell 3, shell 4, shell 5, shell 6, or shell 7. And then the group column or family number tells us how many valence electrons we have in that particular shell, outer shell. Now, how does this relate to bonding? Covalent bonds are composed of 2 electrons. And so the paired electrons are fairly stable, but it will be the unpaired electrons that are going to want to form bonds. And they just need another atom that also has an unpaired electron, and then they can form a bond with that other atom. So the halogens, for example, having 1 unpaired electron are going to want to form a bond here and get some other atom to donate an electron so that there would be 2 electrons here, giving the halogen 2, 4, 6, 8, or what we call an octet of electrons that gives it the electron configuration of the noble gas that's closest to it. Oxygen or sulfur, or those species that are in that group column or family, are going to form 2 bonds because they have 2 unpaired electrons, and they just need another atom that has an unpaired electron to donate here and here. And then oxygen would have 2, 4, 6, 8 electrons, a perfect octet, the same electron configuration as the noble gas closest to it, which for oxygen, that is neon. Nitrogen, having 5 electrons, has 3 unpaired electrons, so would want to form 3 bonds. Carbon has 4 unpaired electrons and would want to form 4 bonds. And as you notice over here, with the halogens, most often they form 1 bond. With oxygen, sulfur, selenium, tellurium, all of the species that are in that group column or family, they're most often going to want to form 2 bonds. Those in nitrogen's group column or family, 5A, they're going to want to form 3 bonds most often because they all have 5 valence electrons. But carbon is a special exception. Carbon always wants 4 bonds. Carbon is like the most spoiled child you can imagine. It will be overly reactive until it gets what it wants, and what it wants is 4 bonds, always. This brings us to talk about drawing Lewis dot structures with compounds. So far, we've been drawing Lewis dot structures with elemental atoms, but we can put those elemental atoms into compounds and draw Lewis dot structures of those compounds. Now, you already know how to determine the number of valence electrons. We've already discussed that. You just go to the top of the group column or family on the periodic table, and the number of that group column or family tells you the number of valence electrons. The connectivity of the chemical structure is the next thing we need to talk about. And in the chemical formula, they typically write the central atom first So if we had a chemical formula like this, AB, with a subscript N, well, there's no subscript on A. That tells us there's only one atom of A. That subscript N could be a 2, 3, 4, 5, or higher whole number, telling us how many atoms of B we have. So suppose we had A, B, and N was equal to 2. A would be our central atom because it's written first, and it would be flanked by 2 atoms each that are B. And so our structure would look like this. If we had N, for example, O2, which is a real structure, then N would be flanked by 2 oxygens, one on either side of it, and the N would be the central atom. The next thing we need to do in order to draw the Lewis dot structure is to determine the theoretical octet, which is the total number of electrons that each and every element on the periodic table wants. Wants 8, unless you're very close to helium, and then you only want 2. But most of those elements on the periodic table want 8 electrons. That makes them stable. And so we can always know what the theoretical electrons are, because for everything except for hydrogen and helium, that number is going to be 8. And for hydrogen and helium, that number is going to be 2, always. Then we need to determine the valence electrons, the total valence electrons. And we know how to get the total valence electrons. As we said up top, we just go to the group, column, or family number, and that tells us how many valence electrons there are for any element. We subtract the total valence electrons, which is what we have, from what we actually want, which is the theoretical octet electrons. Now think about this. If you were going to buy that car, you'd check to see how much money you have in the bank. That's what you actually have. You'd subtract that from the cost of the car, and you'd know how much you needed to borrow. It's the same thing with these electrons. They subtract what they actually have, which is the valence, from the theoretical octet that gives them the electron configuration of the Nobel gas closest to them, and they know how many electrons they'll have to borrow in a bonding interaction. And then you just divide that value by 2 electrons, because there are 2 electrons in each covalent bond. So when compounds are formed, they follow this octet rule, or hydrogen and helium follow the duet rule. Hydrogen, for example, prefers to have 2 electrons. It's electron deficient, and helium will just add to that, because helium is the Nobel gas that is closest to hydrogen. Now again, carbon wants 4 bonds, and carbon can get 4 single bonds, or like in CO2, carbon could have 2 double bonds. Nitrogen wants 3 bonds. Now nitrogen can have 3 single bonds, or like you see here, nitrogen could have 1 triple bond. Oxygen wants 2 bonds because it has, of course, these 2 unpaired electrons, which is what we're talking about in all cases here. That tells us how many bonds a species is going to want. And so oxygen wants 2 bonds. It can do that with 2 single bonds or 1 double bond. Fluorine, which only has 1 unpaired electron, is going to want just 1 bond, and so it will do that with a single bond. Hydrogen and halogens, that would include fluorine, are always terminal. They're never central, because they can't form more than 1 bond. And so in order to be central, you have to be able to form at least 2 bonds. If we look at the connectivity of these particular structures and we evaluate the chemical formula, typically in a chemical formula, the first atom to be written is going to be the central atom in the Lewis dot structure, unless it's starting with a hydrogen. If it's starting with a hydrogen, remember hydrogen can never be central, so we go to the next atom in the chemical formula to see what is going to be central. And the other thing that you'll notice is that hydrogen often will bond with oxygen if there are oxygens in the structure. And we'll talk more about that as we get further along in the course. But for right now, I just want you to remember, and I'll point it out to you when we see them, that this often happens. And it happens because hydrogen is very weak with only one electron that it's barely holding on to. Oxygen is very, very strong, almost like a bully in the chemistry world. So oxygen will bully hydrogen to try to get that one electron away from it. If we look at this first structure on the far left, you can see carbon is written first in the formula, and carbon is the central atom in the structure, flanked by two hydrogens, a chlorine, and a fluorine. The next structure has hydrogen first, and we know hydrogen cannot be central, but the nitrogen can be central. And you may be asking, why is the nitrogen bonded to the three oxygens, but hydrogen is not bonded to nitrogen? And that's because, if you remember, nitrogen has a valence of 5. And so nitrogen has one pair of electrons, and then the other 3 electrons are the positions where nitrogen is going to want to have a bonding partner. The next structure, we seem to have 2 central atoms, and so we have a carbon here that is flanked by 3 hydrogens, and then it's bonded to another carbon, because remember, carbon has to have 4 bonds, always. And then our second carbon is the other central atom, flanked by 2 oxygens and a hydrogen. Again, this carbon is going to have 4 bonds, but you'll learn later that it has a double bond here, a single bond here, and a bond to this carbon over here, giving it a total of 4. The hydrogen, again, hanging around with the oxygen, just like it was doing over here. The next one, we have 2 hydrogens there. So the selenium is going to be our central atom flanked by 2 hydrogens. And then the next one, because hydrogens are first and we know they have to be terminal, sulfur has to be the central atom flanked by 4 oxygens. And then again, you notice the hydrogens are hanging around with the oxygens. They have to be terminal. And then lastly, we have ozone, 3 oxygens. And so one of those oxygens is going to be central, and it will be flanked by the other 2. So let's talk about these rules a couple of slides back and seeing if we can't write a Lewis dot structure for an entire compound HNO3. Now they have this table at the bottom, but when you're doing this, you may want to just write octet electrons and valence electrons like this, and then put a line across. And we're going to determine the octet electrons and the valence electrons, remember, so that we can take the difference between them and see how many electrons we're going to need for sharing. So we start by looking at hydrogen. And we know that the octet for hydrogen or helium, it's theoretical and it's always 2. And we can look at nitrogen, and we know that everything on the periodic table theoretically wants 8 electrons, except for hydrogen and helium. So that means nitrogen wants 8 electrons. And we have oxygen, but we have 3 of them because we have O3. We know that oxygen is not hydrogen and helium, so it's going to want an octet. It's going to want 8 electrons. But we have 3 oxygens, so we have to multiply that by 3. And so the total here is 34. Now we look at the valence electrons. Hydrogen is in group 1A, so it has a valence of 1. Nitrogen on the periodic table is in group 5A, so it has a valence of 5. Oxygen is in group 6A. So it has a valence of 6, but again, there are 3 atoms. And so we have to take into consideration all 3 of those atoms. So that gives us a total of 24 valence electrons, and now we take the difference between those two. And the difference is 10. Now to find out how many bonds we can make with those 10 electrons that we actually have, we're going to divide that by 2 because there's 2 electrons per bond. That gives us a total of 5 bonds for this structure. And so if we draw this structure, hydrogen is not our central atom. It's first, but it's not our central atom. We know that nitrogen has to be our central atom. And we also know that nitrogen is going to want to form 3 bonds because we know that nitrogen alone, its Lewis dot structure, looks like this. So we have 3 oxygens. And then as I told you, one of those oxygens, and it doesn't matter where we put the hydrogen, it could be with any of those oxygens because all 3 of them are chemically equivalent. So one of those oxygens is going to be bonded to a hydrogen. Now, that gives us a total of 1, 2, 3, 4 bonds, and we have 5 bonds. So if you remember, we have oxygen that can have and likes to have 2 bonds. Well, this oxygen that's down here on the bottom has 2 bonds, this one right here. But the other 2 oxygens only have 1 bond. Now nitrogen, remember, likes to have 3 bonds, but it didn't say it has to have only 3 bonds. So we can put a double bond here that gives the oxygen 2 bonds, and I could have just as easily have put that double bond over here. It doesn't matter which side I put it on. I can put it on either side that I want. I'll just put it on that side for the time being. Now there's 5 bonds, and I'm just going to keep going with this to see how this structure works out. And I'll talk to you about how you prove with formal charges whether or not you have a good structure. So now the next thing we have to do is calculate how many electrons to place around the structure in order to give everything an octet or a duet, which is what makes it stable. So we have in our original structure, this is what we actually have, 24 valence electrons. And this is what we've used, 10 of those valence electrons. So we have 24 valence electrons minus 10 equals 14 electrons left that we need to distribute around this structure. So I'm going to look for those species that don't have a perfect octet or a perfect duet. And those are the species that I'm going to give extra electrons to. So this oxygen, since there are 2 electrons in each covalent bond, and this electron has 2, 4, so I'm going to give it 4 more so that it has a total of 8. And then this oxygen is sharing 2 electrons there with nitrogen. So in order to have 8, it needs 6 more. So now I've used 10 of my 14. And then this oxygen is sharing these 2, these 2 electrons with nitrogen, and it's sharing these 2 with hydrogen, and so it needs 4 more. And now I've used all 14 of my electrons, and I want to calculate now the formal charges to make sure that my structure is actually a good structure. So how do I calculate formal charge? The way that I calculate formal charge is as follows. I'm going to take the valence electrons and I'm going to subtract the electrons that are in direct contact with the nucleus. And that's going to equal my formal charge. So let's have a look at this structure down here on the bottom right. And let's calculate the formal charge of the oxygen that has the little blue X in it. So the valence for oxygen, it's in group, column, or family 6A. So the valence is 6. And I'm going to subtract the electrons that are in direct contact with the nucleus. And so I know that I'm sharing 2 electrons, but only one of those 2 electrons is in direct contact with the nucleus. And that is this one. And then I have these 2 and these 2 that are in direct contact with the nucleus, and this one. So just those electrons that are right next to that oxygen. In the sharing electrons that are in bonds with another atom, I'm only taking the one that's closest to my atom. So that gives me 2, 4, 5, 6. And so 6 minus 6 gives me a formal charge of 0. And 0 is what I'm shooting for. In a good structure, you have all zeros. The next best structure, you might have a negative charge adjacent to a positive charge, but the numbers are very low. We like -1 and +1. When we start getting to 2s, we're not happy anymore. So let's calculate the hydrogen now. The valence of hydrogen is 1. And there is 1 electron that is right directly next to hydrogen, so we will subtract that one, and that gives us a formal charge of 0. If we do this oxygen, the valence of oxygen is 6 because it's in group, column, or family 6A on the periodic table. So that is 6 minus, and we're looking for just those electrons that are directly in contact with this oxygen atom. So that's 2, 4, 6, 7. And so that gives us a -1. So we're hoping we see a +1 here somewhere, or this structure isn't as great as it could be. Let's do the nitrogen. Nitrogen is in group, column, or family 5A, so it has a valence of 5. And we see that it has 1, 2, 3, 4 electrons. It has this one, this one, this one, this one, this one, this one, and this one. And so it has 4 electrons directly in contact. That gives us a +1. And then this oxygen over here is 6 minus, there's 1, 2, 3, 4, 5, and 6 in direct contact. And so that gives us a formal charge of 0. This +1, this -1 gives us overall a formal charge of 0, meaning this is a neutral compound, and this structure does work. So this slide is just showing you the rest of what we've already worked out. So I'm going to skip past it, but you may want to look at it at some point. It's telling you divide by 2, the 10 by 2, so that you can get the number of bonds. And then showing you that you use the valence electrons minus those electrons we used for bonding to get the 14 electrons you're going to distribute around the structure. And then showing you the finished structure. And they didn't calculate the formal charge here, but you could calculate it yourself later because I showed you how. And so this is just a summary of all the rules that we've just covered. I'd like to take the time to work out maybe a couple of more Lewis structures so that you get a little bit more experience with it. So let's look at something like methane, which is CH4. So we get our octet electrons and our valence electrons. And we know that carbon wants an octet of 8 because theoretically every element on the periodic table wants an octet except hydrogen and helium, which want a duet. They're happy with 2. So now we have hydrogen, but remember we have H4, so we have 4 of them. Hydrogen is happy with 2, the duet, but there are 4, so we have to take that into consideration. So 8 and 8 gives us a total of 16. And now we look at the valence electrons. Carbon is in group, column, or family 4A, so it has a valence of 4. Hydrogen is in group, column, or family 1A, so it has a valence of 1, but again, there are 4 of them. And so now we have a total of 4 and 4, giving us 8, and when we take the difference, we get 8. We're going to divide by 2 because there are 2 electrons in each bond, and then we get the number of bonds, which is 4. Carbon is the central atom here, and it's going to be flanked by 4 hydrogens. That gives carbon 4 bonds. Now we're going to take our total valence, and our total valence is given here by this 8. Okay, so we have 8 minus those electrons that we've used for bonds. And the electrons that we've used for bonds are, of course, these, which are 8. So we end up with 0 electrons to distribute around that structure. And the math is still working out. So that means that this structure is completed, and now let's just go back and calculate the formal charges. So the formal charge on carbon, we're starting with the valence electrons. Carbon is in group 4A, so it has a valence of 4, and we're going to subtract the electrons that are in direct contact with that carbon, and that is 4. And so that gives us a formal charge of 0. Okay, now let's look at the hydrogens and calculate those. And so hydrogen, each hydrogen has 1 electron that's in direct contact with it. And as you know, hydrogen has a valence of 1 because it's in group, column, or family 1A. So 1 minus the 1 electron that's in direct contact with it gives us a formal charge of 0 for the hydrogens. And so this is a really good structure. That's our completed Lewis dot structure. And I don't mind if you use lines for the bonds. If you have electrons you've distributed around the structure, you need to use dots for those. You need to show those with dots. But if you want to use lines, for example, you could just write methane's Lewis dot structure like this, and that would be fine for me if you use the lines instead of the dots. So now let's try something different. Let's try a species that has a charge on it, for example, like ammonium, polyatomic ion. And let's calculate the octet and the valence electrons and draw the structure of something with a charge. So because ammonium has a +1 charge, that means that ammonium must have lost 1 electron. And so we're going to have to take that away from the valence, not the octet, not the theoretical, because it still wants what it wants. But it lost an actual electron from its valence. So we're going to have to take that away from the valence. So we start with the nitrogen, and we know that it has an octet of 8 because everything on the periodic table wants 8 to be like a noble gas. And then we look at hydrogen, and we know that we have 4 hydrogens. And so the octet for hydrogen is 2 because it's happy with a duet, but there are 4 of them. And so we have a total of 16 here. The valence for nitrogen is 5 because it is in group, column, or family 5A. And the valence for hydrogen is 1 because it is in group, column, or family 1 on the periodic table, but there are 4 of them. And we have one more thing that we have to remember. We have lost 1 electron, so we have to take that away. So this is the total of 9 minus 1 gives us 8. And then 16 minus 8 equals 8. We divide that by 2 electrons per bond, and that gives us 4 bonds. We have a nitrogen that is flanked by 4 hydrogens. Okay, and now we have to calculate our electrons that are going to be distributed around our structure. And so we know that our valence, which is here, our valence is 8. And we used 8 electrons total. So that is 8 minus 8 equals 0. Again, we have no electrons to distribute around this structure. And now we want to calculate the formal charge. So the formal charge on the nitrogen has a valence of 5 because it's in group, column, or family 5A. And in direct contact with nitrogen, there are 4 electrons. So that gives us a +1. And then if we calculate the hydrogens, each hydrogen is chemically equivalent here. They're all bonded to a nitrogen, and they all have the 1 electron in direct contact with them, with a valence of 1 because hydrogen is in group, column, or family 1A, minus the 1 electron that's in direct contact with it. That gives us a formal charge of 0. And each hydrogen is chemically equivalent, so they're all going to have that same formal charge of 0, leaving us with a +1 charge for this structure. And I just want to remind you that we needed that +1 charge because this structure has a +1 on it. When we draw out this structure and we show it as a Lewis dot structure, and again, as I told you, I don't mind if you draw lines instead of dots for the bonds. The proper structure will look like this with a charge outside. Let's try something that might be electron deficient. And so let's look at something like BF3. So your math will hold every time that you have a typical structure, but every once in a while we deviate away from our typical structures and we get some species that is either electron deficient or electron expanded. So just like we had to take care of the positive charge by taking away an electron because it was a +1, we took an electron away from our valence. You can imagine if you had a negative charge, you would be adding that many electrons to your valence. If we have some species that's electron deficient, meaning that it cannot obtain a complete octet, or we have some species that's electron expanded, meaning that it can't either get a perfect octet because it has too many electrons. How do we take care of that? And that's where this math that I'm having you calculate is going to come in really handy, because as soon as the math breaks down, that's when you know you have something that is either deficient or expanded. So as long as the math works, you're good. As soon as the math breaks down and it's not working, you know it's either deficient or expanded. So let me show you an example of that. So again, we're going to do the calculation just like we normally would. And we have boron, which has an octet of 8, or wants an octet of 8. That's its theoretical. And then we have fluorine, which wants an octet of 8. There are 3 of them. So we have to make sure that we take that into consideration. That gives us a total of 32. Now the valence of boron is 3. And the valence of fluorine, being in group column or family 7A, is 7. And we have 3 of them. So that gives us a total of 24. We take the difference between 32 and 24, and that gives us 8. We divide that by 2 electrons because there's 2 electrons per bond, and that gives us a total of 4 bonds. Okay, so we go to draw the structure. We have boron in the middle, and we flank with 3 fluorines, and there's trouble with our math. It's broken down because we only have 3 fluorines. There is no way to have 4 bonds because we don't have another atom to put at the end of another bond. And so we know right away that our math has broken down, and therefore this species we're drawing has to be one of 2 things, either deficient or expanded. Well, we know it's not expanded because it doesn't have more than 8 electrons, so that means that it has to be deficient. We calculate then how many electrons we're going to distribute around this structure, still using our valence. And so when we calculate using the valence, we know that we have a valence of 24, and we have used 2, 4, 6 electrons so far of that. And so that leaves us 18 electrons to distribute around the structure. So we're going to put 6 electrons on each fluorine to give each fluorine a total of 8 with its bonding, shared bonding electrons. And 3 times 6 is 18, and so that takes care of all of those 18 electrons. And now we're going to calculate the formal charge to see if this structure is accurate. So for boron, we have a valence of 3 because boron is in group, column, or family 3A. And then there are 1, 2, 3 electrons in direct contact with it. 3 minus 3 gives us 0. And now since all 3 fluorines are chemically equivalent, we only need to calculate 1 and we'll have the formal charge for all 3. Fluorine has a valence of 7 because it's in group, column, or family 7A. 7 minus, and it has 2, 4, 6, 7 with this one. Electrons in direct contact with it, giving it 0, and so this fluorine has a formal charge of 0, and this one has a formal charge of 0, and this is the correct Lewis structure. And I'll just redraw it over here for you the way that you would want it to look when you turn it in. Although, if I'm asking you to calculate formal charge, etc., I'm going to want to see your work. And so when I say I want to see your work, I'm looking for this, and I'm looking for all of this. let's try another Lewis structure. Let's try something that is expanded and see how that works. So let's look at PF5, phosphorus pentafluoride. And again, we're going to get the octet and the valence. So phosphorus is in group column or family number 5, just like nitrogen. So has a valence of 5, has an octet of 8, because everything on the periodic table wants 8 except for hydrogen and helium. Fluorine is in group column or family 7, but there are 5 of them. So we have to make sure that we take that into account. And fluorine wants, of course, 8. And we have to take into account there are 5 of them. It gives us 48 here. And 40 over here. We take the difference. That is 8 divided by 2 electrons per bond. Gives us 4 bonds. So we set the structure up. Phosphorus is the central atom. We have 1, 2, 3, 4, 5 fluorines. And what we're beginning to see already is that the math has broken down, meaning that we're either expanded or deficient. And in this case, clearly we're expanded because phosphorus already has 2, 4, 6, 8, 10 electrons just in bonding to the 5 fluorines. So we're going to calculate how many electrons are going to be distributed around this structure. Here's our valence, 40, minus these 10 electrons that we already used for bonding. So those are bonding electrons. And that gives us a total of 30 electrons left over. So a total of 40 valence electrons, 10 we've used for bonding, we have 30 left. I'm going to give each one of these fluorines six to give it a perfect octet with the 2 that it's sharing. That uses up all 30 of those electrons, and now we'll look at formal charge. So when we calculate formal charge for the phosphorus, phosphorus has a valence of 5 because it's in group column or family 5. And it's in direct contact with 1, 2, 3, 4, and 5 electrons, giving it a formal charge of 0. And then when we do the fluorines, fluorine has 7 valence electrons because it's in group column or family 7. And we have 1, 2, 3, 4, 5, 6, and 7 electrons that are in direct contact with it, giving us a formal charge of 0, meaning all the fluorines have a formal charge of 0. And so this is a valid structure. So that wraps up the lecture for today on Lewis structures. And knowing this information, you should be able to go forward and do the worksheets that have been posted. You may need to come back to the lecture and start and stop just so that you can remember how we work through these Lewis structures. There are quite a number on the homework, on the worksheets, but it takes a lot of practice to be able to draw Lewis structures and calculate formal charges. And if you need any other help, you can always email me or bring your questions to mentorship on Tuesday and Wednesday evening.